Okay, hello everyone. This is Siddhartha Pramanik. I am a research scholar from the Department of Mathematics, IIT Kharagpur. This is week 7 for the course Introduction to Abstract Group Theory. So, I am supposed to solve some problems related to the content of week 7. First, let me summarize the contents of week 7. Okay, basically in week 6 we have started with group actions, and related to group actions we have saw what do we mean by orbits, and in week 7 we started with stabilizers of elements. Then we have saw a counting formula which relates the cardinality of the orbit and the cardinality of the stabilizer. And this theorem has a name. It is known as orbit stabilizer theorem, which is very important. And after that we have saw one more famous theorem known as Calais theorem. Which basically says every finite group is a subgroup of Sn for some n. So that is why the group Sn is important. And then we have saw orbit decomposition of sets. So we have saw some examples of this. Then we have saw one special type of group action known as faithful group action. And after that we saw conjugacy classes, and we end up with class equations. So more or less this is the main content of this week 7. So first let's start with some examples of stabilizers. Then we will move on to another problems. So in this first problem, I will give some group actions, and the problem is we have to find the stabilizers of those group actions. So find the stabilizer of elements of S in each of the following group actions. So first one is your group is R star comma dot, and your set is Rn, and how the group action here is R dot x1 up to xn is defined as rx1 up to rxn. So we are just multiplying in each coordinate, multiplying r in each coordinate. That is the definition of group action here. So next B, your group is two roots of unity, and your set G is any other group. So how the group action here is defined? So for G belongs to G prime, 1 dot G is G and minus 1 dot G is G inverse. So that is the definition of group action here. So C, so for any group G and a subgroup H of G, let S equals to G mod H. So how the group action is defined? So for G belongs to G and AH belongs to S, G dot AH is just GA of H. So this is the third example, and fourth one is our group G is Sn and our set S is Rn, and for sigma belongs to G and X belongs to S, the definition of group action is sigma dot X is same as just permuting the coordinates using sigma. So these are the four examples. So in previous season we have saw all these four functions are group actions, and also we have determined the orbits. Now we want to determine the stabilizers. Okay, so let's start with the first one. So first one is group is the multiplicative group of non-zero real numbers, and S is the set of all n-tuples of real numbers, and this is the definition of group action. So we need to find the stabilizers of elements. So if so if x1 up to xn belongs to our set S, then what is the stabilizer of this X? So let me write down the definition. So this is the stabilizer, and by definition it is the set of all elements of the group G such that G dot X is same as X. So in our case it is R belongs to R star such that R dot x1 up to xn is same as x1 up to xn. So this is R belongs to R star such that Rx1 comma Rxn is same as x1 up to xn. So from this, what can you say about R?
R is the one.
Uh, Actually, it depends on x. If all xi are 0, then it can be whole R star, right? We need to take care of that. So if x bar is 0, means 0 in all coordinate, then G of 0 means stabilizer of 0 can be whole R star, because whatever you multiply R with 0, it remains 0. But if it is non-zero, means at least in one coordinate you have a non-zero entry, then R star, so then xi is non-zero for some I. So since Rxi equals to xi, so we can cancel xi both from both sides, so that will give you R equals to 1. So in this case g of x bar is R star if x is equals to 0, and it is just singleton set 1 if x is non-zero. I hope you have understood this. And if you remember, in case of orbits, so in case of orbits, uh, the orbit of x bar, it is just multiples of x bar. So it is by definition, right? uh, so this is non-zero multiples of x bar x. So it is actually uh, 0 if x is 0, and it is the whole set when x is non-zero. So you can see if x is 0, then stabilizer is the whole group, so it is very large set. But in case of orbit, it is only singleton set. So that means large orbit if and only if small stabilizer. So that is one thing you should keep remember. So let's move on to another part of this problem. So the second one. So second one, group is the two roots of unity, and our set is any group, and group action is defined by this. So let's see the stabilizers. So for G belongs to S, which is our another group G prime, what is stabilizer of G? So, so first of all, we know that stabilizer, it should be a subgroup of G, which is 1 and minus 1. And it has only two subgroups, right? One is the trivial subgroup and one is the whole group. So this stabilizer has only two possibilities. So in which case it is singleton set, and in which case it is the whole group. So stabilizer of G is first of all, now you look that 1 dot G is G, so 1 definitely belongs to the stabilizer, and it should belong to stabilizer because it is the identity element. But when this minus 1 dot G belongs to the stabilizer, So now minus 1 dot g is same as g inverse. So it will belongs to the stabilizer if and only if minus 1 dot g is equals to g, and that will imply g inverse is equals to g. So this imply g square is identity. So the stabilizer is singleton set if g square is not equals to identity, and it is the whole group if g square is equals to identity. So is it okay?
Yes.
Okay, so let's see the third one. So third one is the group G acting on G mod H by this function. So here G acting on G mod H. So G mod H is S here. So let AH belongs to S, and we need to find stabilizer of AH. So by definition it is G belongs to G such that G dot AH is same as AH. So this is equals to G belongs to G such that GA of H equals to AH, and this is same as G belongs to G such that A inverse GA belongs to H, right? So this is because AH equals to BH if and only if A inverse B belongs to H. You can try to prove this. This is a very basic fact about left cosets. So, and this is same as G belongs to G such that G belongs to A H A inverse. So what can we say about this set? So this is nothing but A H A inverse. So subgroup has a name. If you can recall, this is known as conjugate subgroup of H by A. So this stabilizer of AH is just the conjugate subgroup of H by A. So one thing you can note that if H is a normal subgroup of G, then this conjugate is equals to H. Just a one minute. Yeah, sorry. So, if H is a normal subgroup, then this conjugate is same as H. So in that case, the stabilizer is equals to H itself for all H in S. So I hope this one is also fine. So now let's come to the fourth one, and that is interesting because it's a concrete example. So the group is the permutation group Sn, and the set is the n tuples of L numbers Rn. So group action is just the permutation of the coordinates. So we will try to find stabilizers of some special kind of elements here. So here Sn acts on Rn. So let X belongs to Rn. So we need to find the stabilizer of this element X. We are going to take some special kind of element. So this, let's say it looks like 1 x x up to x, where x not equals to 1 and x belongs to R. So that means in the first coordinate we have 1 and all other coordinates we have x. So what will be the stabilizer of this element? So can you try this?
The permutations which fix one.
Yeah, you are correct. So by definition it is sigma belongs to Sn such that sigma dot x is same as x. So that means sigma belongs to Sn such that x sigma 1 x sigma 2 up to x sigma n is same as x1 up to xn. So that means sigma belongs to Sn such that x sigma of I equals to xi for I equals to 1 to up to n. Now for I equals to 1, uh, so if sigma 1 not equals to 1, then your this 1 can be moved to any other coordinate, right? So then that sigma is not fixing our x, so it cannot be in the stabilizer. So basically, so this is the set sigma belongs to Sn such that sigma of 1 is equals to 1, because in other coordinates all elements are same. So if we permute them, so it does not affect our x. So I hope it's okay. So let's see one more type of element so that it becomes clear. So let's take y equals to 2, 3, x belongs to Rn, where x belongs to R and x not equals to 2 and x not equals to 3. So what is the stabilizer of this y? So try yourself. Yeah, anyone? So
The
similarly,
permutation,
yeah,
the permutation which sends 1 to 2 and 2 to 3.
sigma belongs to Sn such that 1 to 2 and 2 to
Sigma of 2 equal to 3.
no, actually your sigma, so look at the definition. Your sigma should not affect your x, right? So it means whatever sigma you apply, it should fix the first coordinate and the second coordinate. Similarly, it should also fix the other coordinates, but these other coordinates can be permuted in itself. But this first coordinate should be mapped onto it, because if we map this first coordinate, so let's see one example. So let's sigma equals to as you say 1 to 2 and 2 to 3. So let's take this cycle. So what is sigma y bar? So it just permute the coordinates, right? So it sends first coordinate to second coordinate. So that means uh, in your second coordinate you will have 2, and you send second coordinate to third coordinate. So that means in the third coordinate you have 3, and in all other coordinates are fixed. So in all other coordinates uh, you have x, and also sorry, the third coordinate is in the first coordinate, so you have x here, but this is not our element y bar. So sigma is not fixing y, right? So sigma cannot belongs to the stabilizer. So are you getting the point?
Ah, yes, sir. Then is it the one which fixes 1 and 2?
Yeah, so sigma of 1 should be 1 and sigma of 2 should be 2. So that is the stabilizer in this case. So here also sigma belongs to Sn such that x, sorry, in this case we have y sigma I is same as yi for I equals to 1 to n. But this from third coordinate to nth coordinate, we can permute those elements because all elements are same. But this first and second coordinate are distinct. So we have to fix them. So this is sigma belongs to Sn such that sigma of 1 is 1 and sigma of 2 is 2. Yeah. So let's see one more example so that it becomes clear. So let's take z bar is 2 2 x x up to x, where x is not equals to 2. Now just tell me what will be the stabilizer of this element. So what is this set? So observe that these first two coordinates we can permute among these first two coordinates only, and these other coordinates can be permuted among itself. So sigma of 1 2 must maps to this set, and sigma of the other set, it can be anything. We don't know about this, but we must have this condition. So here sigma belongs to Sn such that sigma of this set is equals to 1 comma 2. But observe that here we can map 1 to 2 and 2 to 1 because we have same entries in the first two coordinates. We can permute them among itself. And similar for the this other coordinates, we can permute among themselves. So did you understand this?
Yes, sir.
Others, do you have a doubt?
Yes, sir, clear.
Okay. Okay. So let's move on to different type of problems. So we have heard about faithful accents, right? So when a, let's say G is a group acting on a set S. So when it is faithful, so if G dot S is S for all S belongs to S, and that implies G is equals to the identity, then we say it is a faithful action, right? So let's see some example for this, some quick examples. Okay, let's keep this. So check whether the following examples, following group actions are faithful or not. Okay, let's take the first example in the previous one, where G is R star comma dot, and S is the set Rn, and the action is defined by just multiplication by R in each coordinate. So is it faithful? Can you check? Did you understood the definition of faithful action? So if for some element G, G dot S is S for all S in S, then that G has to be identity. In that case, we say it is a faithful.
It is not faithful.
Uh, why? Can you explain?
If we take every element as 0, then G can be any number.
No,
It gives the same.
G dot S equals to S for all S belongs to S. This should be true. So do you have some R belongs to R star? So the question is, does there exist some R belongs to R star such that Rx equals to X for all X in Rn. So definitely R is 1. 1, we can take 1. But are there other element?
No other elements.
Yeah. So only element which satisfies this condition is 1, which is the identity element of this group. So it is faithful by definition. So R dot xn equals to x1 up to xn for all x1 up to xn belongs to Rn, that will imply R is 1. So it is faithful. So this, for these things you just have to exploit the definition, nothing else. So one more example. So what about the our last example where G is Sn and S is Rn. And the group action is just the permutation of coordinates. Is it faithful? So uh, does there exist a non-identity element sigma in Sn such that sigma of x equals to x for all x belongs to Rn? So does there exist any non-identity permutation sigma which does not permutes the coordinates of any element of Rn? There exists no element, right? Because if you simply so it is no, because if sigma is non-identity, then let's say sigma of I is equals to j for some I not equals to j, and ij is just belongs to the set 1 to n, means sigma sends I to j, right? So you just take x is equals to some 1 and here some 2, it is the ith coordinate and it is the jth coordinate, and the rest other things coordinates you can take anything. So let's take 0. So 0. So then what is sigma of x? Is it equals to x? It is not, right? Because the ith coordinate and jth coordinate are interchanged. So then sigma of x is 0, 2, so this is not equals to x. So only element that satisfies this definition is the identity permutation. So it is also faithful. So it is a faithful group action. Okay, I hope this is clear for you. Now let's see one theoretical problem. So we all have seen Cali's theorem, right? Also the proof of Cali's theorem. Now I will do one more general thing. From that Cali's theorem will follow. So this is known as permutation representation of a group action. Okay, so before that, one thing. So we know Sn is the group of all bijections from 1 to up to n to itself, right? But instead of this set 1 to up to n, if we take any arbitrary set and take its bijection, then that is also a group. So for any set x, the set sim of x of all bijections from x to itself. So this set is also a group where the group operation is composition of function. So these similar groups. So this is for just 1 to up to n. This is for any set x. So I need this fact. Okay. So we were doing permutation representation of group action. So what does it says? So let G be a group acting on a set, let's say S. So S is a set, then we can consider the group symmetric group of S, means the set of all bijections from S to itself. So this says then there exists a unique group homomorphism from G to the group symmetries of X S. Okay, let's do a quick proof. I will not do all details because you have already done Cali's theorem. So same proof will hold here. So uh, now G acts on S, right? So that means we have a function from G cross S to S, right? So which sends G comma S to GS, and this satisfies two properties. First one is E dot S is S for all S belongs to S, and second one is G1 dot G2 dot S is same as G1 G2 dot S for all G1 G2 in G and S in S. So observe that this is a function of two variables. Means the domain is Cartesian product, right? So if we fix the first coordinate, then it is a function of one variable. So that means so for a fixed element G belongs to G, what is this map then? The map, uh, the function means we have a function, we have which sends a function from S to S. So how it is defined? Where X sends to G dot S. So let's give a name to this function. So let's name this by phi suffix G from S to S, and it is defined by phi suffix G of S is just G dot S. So we are just fixing the first coordinate of this function. So I hope you have understood this. So then phi G is a bijection of S. This thing is exercise for you. You can check by yourself, or you just imitate the proof of Cali's theorem. So then phi G belongs to the set sim of S. So for each element of G, of the group G, we have an element of this group sim of S. So that means we have a function. So define f from G to sim of S by f of G as the function phi of G. So we have a function. So you can check that this is a group homomorphism. Then f is a group homomorphism. This will follow from these two properties of group action. So you can check it by yourself. And this is also unique because it depends on the group action. So from this we end this result. But the interesting fact is, so here we have taken any arbitrary group action, right? Where S can be any set, and this group action can be anything. But if we take S as G itself, and the group action is the left multiplication, then you will have the Cali's theorem. So first fact is, if we take S is G and the group action as okay, and we need to take G is a finite group, right? So otherwise Cali's theorem does not make sense. So and the group action as left multiplication of G on itself, then we have the Callis theorem. Provided G is a finite group. So that is one thing. And the second thing which is also interesting, so provided a group action, we have a homomorphism. And the second fact is the converse of this result is also true. So what is the converse of this result? So converse of the result is also true. So can anyone say what is the converse or guess anything at least? So you have understood this result, right? Or do you have any doubt? Okay, I hope you have understood. So let me write down the converse. So here I am saying if we have a group action, then we have a group homomorphism. This is our result. Now the converse is if we have a group homomorphism, then that will also give you a group action. And that result will give you some interesting facts. So let me write down the converse first. So see the following. So this is 3, so it's problem number 4. So let G be a group and S be a set. So suppose F from G to the seam of S is a group action. Sorry, is a group homomorphism. Then there exists a unique group action of G on S. So we have a group G and a set S and a group homomorphism from G to symmetric group of S. So this will induce a group action of G on S. So let's see a quick proof for this. So group action means a function from G cross S to S which satisfies two properties, right? So let's first try to give a function from G cross S to S. So define this G means the G dot S as f of G. So G is the element of the group. So f of G is an element of the symmetric group. So this is f of G is a bijection of S. So we can see where S is going under f of G. So let's define this function. and we are claiming that this is a group action. So claim the above function is a group action. So let's quickly check two properties. So uh, this is very easy actually. So what is E dot S? So E is the identity element of G. So it is just basically f of E of S. Since F is a group homomorphism, so f of P should be identity of symmetric group of S. So this is a identity function on S, right? So we are evaluating small s at small s. So since this is identity function, this should same as S. So first property is true. Now what about the second one? So let's take G1 dot G2 dot S. So by definition, this is f of G1 evaluated at G2 dot S. And this is same as f of G1 evaluated at f of G2 evaluated at S. Now f of G1 is a sorry. Uh, Now we can write this as f of G1. This is a bijection in S, bijection of S. F of G2. This is also a bijection of S. So this is a composition of two bijections. So we can evaluate it at S. But this is same as f of G1 times G2 because F is a group homomorphism. So this is same as G1 G2 dot S. So we have a group action. So I hope this proof is clear. Uh, Sorry, just a minute. Yeah, sorry. So this is a group action. So this completes the proof of this problem. So the interesting fact is, so if G is a group and S is a set, then there exists a bijection between these following sets. Between the following sets. So first one is the set of all group actions of G on S, and the other set is the set of all, here also the set of all group homomorphisms from G to sim of S. So these two sets are in bijective correspondence. So these two sets has the same cardinality, right? So I hope you have understood this. So this remark follows from the previous two problems. So you just remember that these two sets are in bijective correspondence. So let's see a quick application of this. So find how many group actions of Z mod 5Z on a set on the set, let's say 1 2 3 are there. So you need to find the total number of group actions of Z mod 5Z on this set. What is the total number of group actions of Z mod 5Z on this set 1 2 3? So can you do this? So here our G is Z mod 5Z and S is the set 1 2 3. So how many group actions of G on S are there? The number. You need the total number. Just use this bijective correspondence. Using this, do you have any answer? So here the symmetric group of S is nothing but S3, right? So the total number of group actions of G on S is equals to the total number of group homomorphisms from G, which is Z mod 5Z, to S3. So can you find this? How many group homomorphisms are there from Z mod 5Z to S3? Okay. So now if F from Z mod 5Z to S3 is a group homomorphism, then now observe that Z mod 5Z is a cyclic group of order 5 and 1 is a generator of Z mod 5Z, right? So order of 1, so order of 1 is 5. So order of f of 1 bar should divide order of 1 bar. This is the property of group homomorphism. So this implies order of f of 1 bar divides 5, but 5 is a prime number. So order of f of 1 bar is either 1 or 5. So in S3, do you have any element of order 5? No, right? It has only elements of order 1. So let's write S3. So S3 is identity 1 2, 1 3, 2 3, 1 2 3, and 1 3 2. Identity element has order 1. These are 2 cycles, so they have order 2. These 2 are 3 cycles, so they have order 3. So it has no element of order 5. So order of F1 bar must be 1. So that implies F of 1 bar should be identity element. But 1 bar is the generator. So if you send generator to identity element, all other element must be identity. So F of A bar is identity for all A bar belongs to Z mod 5Z. So that imply F is the trivial group homomorphism. So that implies we have only one group homomorphism from Z mod 5Z to S3. So there exists only one group homomorphism from Z mod 5Z to S3. So there exists only one group action. Is it okay?
Yes.
Okay. So in this way, you can find the total number of group actions also. If you can find the number of group homomorphisms. Okay. So we have done stabilizers. We have done Callis theorem. We have done faithful action. Now let's see some problems in conjugacy classes. So this was problem number 5. So this is problem number 6. So now in next couple of problems, we will see how the elements, conjugate elements in the group Sn looks like. So it is conjugacy in Sn. So this is important because every group is embedded in Sn. So it is something like enough to study Sn. Something, but not all cases. So first result in this related is so let sigma is the k cycle belongs to Sn and tau be any other permutation in Sn. Then tau sigma tau inverse, it is also an element of Sn, but it is a conjugate of sigma, right? And the interesting fact is we can compute this conjugate element by just knowing sigma and sorry, it has a special structure. So this is looks like it is a cycle, it is also a k cycle, tau of a1, tau of a2, tau of ak. Means we are just observing where this first index a1 goes under tau, the second index a2 goes under tau, similarly dot dot up to last index ak goes under tau. So let's see a quick proof for this. So we need to prove tau sigma tau inverse is exactly this k cycle. That means this permutation tau sigma, let put a name, let alpha equals to tau sigma tau inverse. So then we need to prove alpha sends tau of a1 to tau of a2, and then tau of a2 to tau of a3, continuing in this way, tau of ak to tau of a1. So then only it will be a cycle, right? So then alpha of tau a1, what is this? So this is tau sigma tau inverse of tau of a1. Now tau inverse and tau, this is identity. So this is tau sigma a1. Now under sigma, a1 goes to a2, right? Here a1 goes to a2. So this is tau of a2. So similarly, alpha of tau ai is tau ai plus 1 for I equals to 1 to up to n minus 1. And what about tau n plus 1? Sorry, tau an. So tau alpha of tau of an is same as tau sigma tau inverse of tau of an. Now this is tau of sigma of an. Now what is sigma of an? Sorry, a k. Sorry, I need to take a k.
K everywhere.
Yeah. So it is k minus 1. It is k. My mistake. So sigma of ak is just a1.
Go to A1.
So it is tau of a1. So alpha sends tau of a1 to tau of a2 and so on, tau of ak to tau of a1. And if let's say a does not belongs to tau of a1 up to tau of ak, then we need to show, then we need to show alpha of a equals to a. Then only alpha will be k cycle of this line, of this form, right? So So A does not belongs to this set. So what does it mean? That means A is not equals to tau of AI or I equals to 1 to up to k. That implies tau inverse of A is not equals to AI or I equals to 1 to up to k. Right? So what is alpha of A? It is same as tau sigma tau inverse of A, but tau inverse of A is not AI. So sigma must fix all other indexes. So this implies tau of tau inverse A, since sigma fixes this index and this is equals to A. So hence alpha is tau A1 dot dot up to tau AK. So this completes the proof. So I hope it is okay. So important thing is to remember this formula. So if you have a K cycle, then how to find this conjugate? So let's see quickly two examples to digest this. So let sigma is 2, 7, 9 and tau is 1, 2, 5, 6, 7 and 3, 9. So sigma and tau you can assume they are in S10. So then what is uh, tau sigma tau inverse? Can you say what is tau sigma tau inverse by using the formula? So sigma is a 3 cycle. So its conjugate, it is also a 3 cycle by the previous formula. But what is this? So it is tau of 2, tau of 7, tau of 9. So it is this 3 cycle by the formula. So what is this?
One, five, three.
Yeah, so it is 1, 5. Okay, so I hope you have understood this formula. Now, using this, we have found conjugate of a cycle. So more generally, we can found conjugate of any permutation. So let it is B. So if sigma and tau belongs to Sn and sigma equals to sigma 1 dot sigma 2 up to sigma k is the disjoint cycle form. Okay, we don't need disjoint cycle form. Just and sigma is the product where sigma i's are just cycles. So then tau sigma tau inverse is tau sigma 1 sigma k tau inverse, right? Now this is same as tau sigma 1 tau inverse dot dot up to tau sigma k tau inverse. So these are also cycles, and we can compute the conjugate of cycles. So let's see an example. So let sigma is just let's take easy one, 1 2 3 4, and tau equals to 2 3 3 2 5 1 4. So what is tau sigma tau inverse? So it is tau the cycle 1 2 tau inverse, again tau 3 4 tau inverse. So it is also a two cycle, it is also a two cycle. Now what is these two cycles? It is tau of 1 tau of 2, and this one is tau of 3 tau of 4. So under tau 1 goes to 4, so it is 4 4 5, and this one is tau of 3 is 2, tau of 4 is 1, so it is 2 1. So is it okay? Did you understood this?
Yes.
So now we are in a position to state one big result in SN. So the question is, if sigma and tau belongs to Sn, so when this sigma and tau can be conjugate to each other. Okay, we will answer this question. So one thing you can observe that, so sigma first in the first problem, if sigma is a k cycle, then its conjugate is also a k cycle. So whatever the cycle structure sigma has, the same structure its conjugate has. So an element and its conjugate basically has the same cycle structure, disjoint cycle decomposition, and the converse is also true. So okay, let me write down the result. Two elements sigma and tau belongs to Sn are conjugate to each other if and only if sigma and tau has the same cycle structure. So that means uh, if we write sigma as sigma 1 up to sigma k, this is, and tau as tau 1 up to tau r, so this is disjoint cycle decompositions. Suppose sigma I is ki cycle. So then R has to be equals to K, and some tau J is Ki cycle. So if here you have some product of cycles, right? So the same kind of product of cycles is also here if they are conjugate. So that is the thing I want to mention here. So let's see a proof for this. So one side proof is clear by the first two part. So if sigma and tau has are conjugate, that means tau is equals to some alpha sigma alpha inverse for some alpha in Sn. So then they has the same cycle structure. Then they has the same cycle structure by, let's say, A and B. So we need to prove the converse one. So conversely, suppose uh, sigma and tau has the same cycle structure. So we want to prove their conjugate. Prove sigma and tau are conjugate. So same cycle structure means, suppose sigma is product of a 2 cycle and a 3 cycle. So then tau is also a product of a 2 cycle and 3 cycle. May not be the same cycles, but cycles of same lengths. So that is the case. So now let's say sigma is equals to sigma 1 up to sigma k, and tau is equals to tau 1 up to tau k. These are the disjoint cycle decompositions. So we need some alpha belongs to Sn such that sigma is equals to alpha tau alpha inverse. So that means alpha tau 1 alpha inverse, alpha tau 2 alpha inverse, dot dot alpha tau k alpha inverse. So that means it is sufficient to prove that the cycle of same lengths are conjugate. So it is enough to prove cycle of same lengths are conjugate. So let sigma is a k cycle a1 up to ak, tau is also a k cycle, b1 up to bk. So we want to prove these two are conjugate. So can you give some alpha such that sigma is alpha tau alpha inverse? Can you give? By using our first result? So see, so set, so we want sigma is equals to alpha tau alpha inverse, right? Now what is alpha tau alpha inverse? It is same as alpha of b1 dot dot alpha of bk, but we want this is equals to a1 up to ak. So let alpha equals to alpha b1 a1, these two cycle, alpha b2 a2 up to alpha bk ak. So then alpha tau alpha inverse is same as alpha b1 up to alpha bk, right? This is by our first result, but this is same as a1 a2 up to ak. Okay, so this completes the proof. Is it okay? Okay, so we know in Sm which elements can be conjugate to each other, right? So they are conjugate if and only if they has the same cycle structure. Now using this, let us find the class equation of S3, S4 and maybe other. So it is problem number 7. So okay, let's see first some examples. So in S3 we know the elements are 1 2 1 3 2 3 1 2 3 1 3 2. So here which elements are conjugate? So here identity is conjugate to only itself. The element 1 2 1 3 2 3 are conjugates because they are all two cycles, and other 1 2 3 1 3 2, these are conjugates because these two are three cycles. Okay, now what about S4? So S4 has 24 elements, so I am not going to write all 24 elements. So 1 2 3 4 and 1 2 3 4. So is these two elements conjugate? Anyone? These two elements are conjugate or not?
No.
Yeah, because this is product of two cycles and this is a 4 cycle. So they has,
I think
yes, so
they
they
are
has
different.
different cycle structures. So they cannot be conjugate. And one more thing, conjugate elements has same order. So here this is a 4 cycle. So it has order 4 and this has order 2. So these two elements cannot be conjugate. So this and this are not conjugates. Okay, now let's find class equations. So let's see class equation of S4. So let me recall what is the class equation. So if G is a finite group, so let G acts on itself by conjugation. So then order of G is same as order of distinct orbits. Let's say I equals to 1 to S, right? So this is the our class equation. But in case of conjugation action, the orbits are just conjugacy classes. So these are, so what is conjugacy class of X? It is the set of all conjugates of X. Okay, so this equation is class equation of a group. So we have already seen class equation of S3, right? So it is 6 and we have saw 6 equals to 1 plus 3 plus 2. So you can check. So conjugate of identity is just identity. So its conjugacy class has one element. These three are in the same conjugacy class. So we have 3 and these two are in same conjugacy class. So we have 2. But what about S4? So to determine the class equation of S4, we need to determine the cardinality of the different conjugacy classes. That means we need to determine different, how many elements of different cycle structures are there. So we need to determine the cardinalities of different conjugacy classes. Of different conjugacy classes in S4. So conjugacy classes are set of all conjugate elements of some element. But these elements has the same cycle structures, right? So first we need to determine all possible cycle structures in S4. Then we will find the order of conjugacy classes of those cycle structures. So let's make a table for that. So here we have cycle structures. Here we have number of elements in that cycle structure. So in S4 we have 4 indexes. So we have one cycle, and one cycle means the identity. So we have only one element. So we have 2 cycles. So in S4 how many 2 cycles are there? So let's we'll make the number letter first, completes the left hand side of this table. So we have 2 cycles, we have 3 cycles, we have 4 cycles, and we have product of 2 cycles. So only these 5 types of elements are there in S4, right? There is no other cycle structures. I hope is this is clear. So this type of cycle structure means the one cycles we have only one element, which is the identity. Now the number of 2 cycles.
6.
Yeah, so 2 cycles means it is of the form A comma B. So A has 4 choices, B has 3 choices, but a 2 cycle can be written in 2 ways. So we
And
will
they
divide it by
also
2.
interchange.
So it is 6. Similarly for 3 cycles, it has 4 choice, it has 3 choice, it has 2 choice, and a 3 cycle can be written in 3 ways. So we divide it by 3. So it is 8. Now the number of 4 cycles. So you can see it will be 4 factorial by 4. So it is 4 factorial by 4. That means it is 6. Now number of elements of this form. So it is of the type AB times CD. This has 4 choice. This has 3 choice. But it is a 2 cycle, so we'll divide it by 2. This has 2 choice. This has only 1 choice. Again this is a 2 cycle, so we'll divide it by 2. But these 2 cycles can commute with each other, so we'll divide it by again 2. So ultimately this number is 3. So what is the class equation? Just add this number. So cardinality of S4 is 24. You can check that this should be 24, and the class equation is 24 equals to 1 plus 6 plus 8 plus 6 plus 3. So this gives the class equation of S4. Is it okay?
Yes, sir.
So similarly, you can try the classification of S5. So here we have uh, 5 possibilities. In that case, you will have 7 possibilities. Just find the number of elements and make that table, and you will get the class equation. So in case of Sn, that is not much difficult. So so we have found the class equation of S4, and also we have seen the classification of S3 in the lectures. Now I want to do one application of this conjugacy results in Sn. One more application. That is interesting problem. So 8. So let sigma is equals to 1, 2, 3, 4 belongs to S6. Okay, then find the cardinality of centralizer of sigma. So I hope you know the definition of centralizer. So centralizer of sigma is alpha belongs to, okay, let me write the general definition. So if G is a group and G belongs to G, then centralizer of G is the set of all elements of G which commutes with G, and conjugacy class of G is the set of all conjugates of G. Okay, I hope you can recall this definition. So can you do this problem? Do you have any idea how to do it? So to do this problem, we need that counting formula, that orbit stabilizer theorem. So let me recall that for you. So it is a good exercise to recall all the things. So recall, this is the first one, and second one is orbit stabilizer theorem. So what does it says? So if G acts on S, then for S belongs to S, okay, we need okay, okay, we need G to be finite. Let G be a finite group, and G acts on S. Then for S belongs to S, order of G okay, not G, order of G quotient by order of stabilizer of S is same as order of cardinality of orbit of S, right? This is because there exists a bijection from this G mod Gs to orbit of S. So I hope you have seen this in the lectures. So we need this thing, this counting formula. Also recall one more thing. If G acts on itself by conjugation, then how the orbits and stabilizers looks like? Then for G belongs to G, what is the orbit? Orbit is AGA inverse such that A belongs to G. So this is same as the conjugacy class of G, and stabilizer of G is A belongs to G such that AGA inverse is G. So this is A belongs, sorry,
Certainly.
yes, it is centralizer. So A belongs to G such that AG equals to GA. So it is centralizer. So orbits are the conjugacy classes and stabilizers are the centralizer. So from this we have got the class equation, right? Now use the orbit stabilizer theorem in this action. So let me write it. So by orbit stabilizer theorem, order of G is same as uh, order of conjugacy class of G times order of centralizer of G, or maybe the other way, uh, just in the same form what we have done. Order of G by order of the centralizer of G is same as the order of the conjugacy class, right? Now let's come back to our problem. So we have an element, we need to find the cardinality of the centralizer of that element. So we know this is our G, this is the centralizer. So if we can find this order of this conjugacy class, then we can find this term also, right? So let's try to find the order of the conjugacy class of this element. So can you find this? So now come back to our problem. So order of S6 by order of, yes, anyone have any answer? So
Number of conjugacy classes is 45.
okay, you are saying this is 45. Okay, let's quickly check. So this is product of two cycles. So all the conjugates, now, okay, let me write. Now conjugates of sigma has the form let's say A, B, C, D, because they should have the same cycle structure. Just remember that thing because that is useful. So we need to found total number of elements of this type. So again, this has 4 choice, this has, sorry, this has 6 choice, this has 5, this has 4, this has 3. It should be divided by 2 because of 2 cycle. Same reason, here should be 2, and these 2 cycles can commute. So you will again divide by 2. So this is equals to 45. Yes, so you are correct. So and the total number of elements of this form is 45. So the cardinality of the conjugate class is 45. Hence, uh, cardinality of the centralizer of sigma is cardinality of S6 by,
16.
yeah. So it is, you are saying it is 16. Okay, so you can check, it is not difficult because it is just 6 factorial by 45. So you can check whatever it is the case. So that is not the big thing. The big thing is to find the cardinality of the centralizer. So I hope you have understood how to find the conjugate elements, how to find the cardinality of the conjugacy classes, and finally the class equation. And also this problem is good because it involves so many things: orbit stabilizer theorem, the conjugation action, so many things, and the results of conjugacy in SN. So let's see if I forward some topic. Yeah, so we have done conjugacy classes, class equation, faithful action. Yeah, so I think I have covered almost all the topics in the previous week. So do you have any other doubt in this week?
No, sir.
Yeah, others?
Sir, can you give some more example for finding class equation?
Class equation in of SN or in other group?
Other than SN.
Like what group do you thought?
I couldn't get you clear.
So in the lectures, you were not introduced with other interesting groups. Like there is one group known as DN. Also, there is one group Q8 known as quaternion group. So I can do class equations of Dn for n odd, because for n even that is tough. But you were not introduced with these groups, so I don't know you are aware of these groups or not. But I can do the class equation of Q8 because introducing this group is not difficult. So one thing I can do is in the next season, if you are there, I will introduce this group Q8 and I will find the class equation of this group Q8.
Okay.
Yeah. So if I forgot that, you can remind me. I will do that. So any other question?
Sir, I have one
Yeah,
question.
you can ask.
Sir, sir, what do you mean by size of a conjugacy class, sir?
Means the cardinality of this set, which is conjugacy class. Cardinality of this set.
Sir,
Yes.
sir, what is this, sir? Cardinality of
Cardinality of this set, conjugate class of G.
sir, sir. Size means cardinality of the set.
Yes, yes, yes. Cardinality of this set.
Okay, sir. Thank you.
Yeah. Any other thing?
Thank you, sir.
Yeah. Because we have only one more week left. So if you have any doubt, you can ask. If you have no doubt, then maybe we can stop here. Okay, then since it seems you have no doubt, then I think it is better to stop here. So thank you for joining. We will meet in the next week.
Thank you, sir. Thank you.